Hello, this is Jake Abbott, and today we're going to be talking about functions of a square matrix. There's a lot of math that you can do on square matrices that you can't do on matrices in general, and those mathematical tools are going to be really important to us in analysis of state space systems. So let's begin with some really simple matrix math for square matrices. So let's say I have a matrix A, and let's just say it's a little 2 by 2 matrix of some constant A, B, C, and D, like this. Now, this idea of A squared is something that's really well established, and it's sort of obvious how you would do that. You would just multiply A, B, C, D times A, B, C, D. But the one thing that maybe isn't completely obvious until you write it out like this and start doing the multiplication is what A squared is not equal to is it's not equal to A squared, little b squared, little c squared, like this. So this might be kind of obvious actually in this case that yeah, the way when I say A squared, what I really mean is I'm multiplying A by A. And we could do that, A to the k power, where if it were if it were A cubed, you would say, well, that's just A times A times A, and you'd multiply these one at a time. And just even beginning to look at this A squared as a really simple function, you start seeing why we're talking about square matrices here. Because in general, if A is not a square matrix, you can't multiply it by itself because the inner and outer dimensions won't match up. So this sort of thing only makes sense for square matrices. So we see that when we're talking about at least the simple function of multiplying matrices by each other, the way we do it is we just explicitly write out the matrices and multiply them. We don't do term by term multiplication. It does turn out, though, that if A is equal to a diagonal matrix, so let's say this was a zero term here and here, so you just had A like this, then when you do all the term by term multiplication, you see that A squared does equal to little a squared and little d squared. And it turns out that's actually true of not only diagonal matrices, but block diagonal matrices. So if A was equal to some little matrix A1 here and some other matrix A2 here, and they're all big zero matrices here, so we had some block diagonal matrix, and they don't even all have to be the same. I mean, this could be like a 2 by 2 matrix, and this could be a 3 by 3 matrix, but all square. But by saying block diagonal, it means that you're only looking at square. Then in this case of block diagonal matrices, it's also the case that you can multiply the individual blocks by themselves, and the individual blocks get multiplied back up to the traditional, write them out, and multiply them by each other. So that's how multiplying, just doing a squaring operation and cubing operations work. It turns out for more general functions, so let's say that we have some function of x, and it's a polynomial of x. So let's say f of x is equal to x squared plus 2x plus 3. There's some polynomial of x where you've got x to a bunch of powers of itself. Then this sort of function, a function that's a polynomial of x, is also defined for square matrices. So I can feed that same function a square matrix as its input, and then you just plug in the matrix in every place that the original variable was. Now, of course, I have to stick an identity matrix here because I can't multiply the number, or I can't add the number 3 in general to a matrix. So this is the way that this translates. But because we know how to take A to any power, it's pretty obvious that a polynomial function of x is sort of well defined in this way. And then the same thing goes for block diagonal matrices. So let's say I again have A as a block diagonal matrix. So there's one block there, and there's one block there. And I want to take this function f of A. Well, that ends up being, I can take the functions of the individual blocks, like this. And they're all going to have the same dimension, so the function of the matrix has the same dimension as the matrix, and you can see that here. If A is an n by n thing, then f of A is also an n by n thing, and I'm adding a bunch of n by n matrices together. So these sort of functions of just polynomials are defined for matrices. And you can easily prove these to yourself if you want to just work through some simple examples. So we've been talking about similarity transformations in earlier videos, and let's remind ourselves what we meant when we said that we were doing similarity transformations. We said that I can find some matrix A tilde that's similar to a matrix A using some similarity transformation like this. And because of the way that Q is invertible, we have that I can also write this as Q A tilde Q inverse equals A, and these are sort of equivalent statements because of the way Q is invertible. So what happens if I look now at A squared? Well, A squared, I'm just going to plug in this for A squared, so I'm going to get Q A tilde Q inverse for the first A, and then Q A tilde Q inverse for the second A. And then I acknowledge that these two in the middle are just the identity matrix, and multiplying things by the identity matrix don't change them. So it's like this just disappears. And so then I'm left with Q A tilde Q inverse. But that's just equal to Q A tilde squared Q inverse. And so I say that A squared is Q A tilde squared Q inverse. And if I would have said, what's A to the fifth, I would have gotten Q A tilde to the fifth Q inverse. So if I want to do similarity transformations, I can basically, I don't have to raise the Q's to the power, only the A's in the middle, because this will keep happening over and over, that I'll get Q inverse times Q, and those will drop off. And all you're left with is the Q and the Q inverse on the outside. So this equation works for any number k, A to the k power. And it also turns out, using the same sort of function math as before, it turns out that if you want to have some function of A, and that's going to equal Q times the function of A tilde, Q inverse. And this is completely equivalent to saying that the function of A tilde is equal to Q inverse function of A, Q. And you can also easily prove this to yourself, that this is true, and it's using the same sort of proof that we just did above here. So there's an interesting thing we can do for square matrices too, a really powerful theorem to use when you're trying to prove yourself different properties mathematically, and it's called the Cayley-Hamilton theorem. And the Cayley-Hamilton theorem looks like this. So if we have some matrix A, and it's an n by n square matrix, then we've been talking about its characteristic polynomial. And its characteristic polynomial, you just take the determinant of lambda I minus A, equals the determinant of lambda I minus A, and you can also say A minus lambda I, it doesn't matter, and you set that thing equal to 0. This is the characteristic polynomial, and that characteristic polynomial always has this sort of shape. It looks like it's an nth order polynomial in lambda, so I'll have lambda to the n plus some alpha, which is just some scalar constant, times lambda to the n minus 1 power, and then I'll have a bunch of additional terms, and then I'll eventually get to alpha n minus 1 lambda plus alpha n. So I have an nth order polynomial in lambda, and I need n coefficients alpha to describe this polynomial, and that's equal to 0. So we call this the characteristic polynomial, or characteristic equation of this n by n matrix A. Well, what the Cayley-Hamilton theorem says is, it says if I take this polynomial that's a scalar and I plug in the matrix itself into this function, so I have this delta A like this, so I'm just plugging in this matrix in each spot. So I'll have alpha 1, A to the n minus 1, alpha n minus 1, A, and then I have to have an identity matrix here, an n by n identity matrix, just to make the dimensions match up. that this is also satisfied. And the way that you can remember the Cayley-Hamilton theorem, and it's often said as an English sentence, you don't even hardly have to remember the mathematical proof. The way people talk about the Cayley-Hamilton theorem is they say a matrix A satisfies its own characteristic polynomial. Meaning, if you take A, solve for its characteristic polynomial, and plug A into that characteristic polynomial, it actually will equal 0. So a matrix A satisfies its own characteristic polynomial. So that's the Cayley-Hamilton theorem. So we've been talking about these kind of simple polynomials and saying that square matrices satisfy these simple polynomials. But it turns out that lots of other functions that aren't at first obvious how you would solve them with matrices are also solved. And so, for example, one is a sine function. So if I have sine of x, it isn't obvious necessarily how you would solve for sine of a. So let's say a again looks like little a, little b, little c, little d. And sort of a naive solution would say, well, what is sine of the matrix A? Well, we know how to do signs of scalars, or at least you know how to plug them in your calculator. I mean, sometimes if you didn't have a calculator and I said, what's the sine of 7? I'm not sure, you can necessarily solve for it. So a naive assumption is to say, well, at least I sort of know how to get signs of scalars, so I'll do something like this. But based on our discussions earlier about how you would do a squared, I think it's sort of, probably pretty safe to say that's not true, and it isn't true. This isn't the way you properly solve for sine. So how is sine solved? Well, sine is solved by going back to a Taylor series approximation for sine of x. So sine of x, if you remember, looks like x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and this goes on to infinity, where you're alternating like this. So once you realize that sine is a function that's written like this as some sort of polynomial, then you say, oh, okay, I've seen this before, and I know that a polynomial like this, I can just plug in a, and so this is the way that you would solve for sine of a, is you would solve it using this Taylor series approximation. A minus a cubed over 3 factorial, dot, dot, dot. So you're just going to plug in the a right into this function. And it turns out there are other functions that this works for as well. So, for instance, cosine of x, what's its series approximation? 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus dot, dot, dot. Another common function, and probably the most important function for our purposes, is an exponential function, e to the x. It looks like 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot, dot, dot. The exponential function series is the easiest to remember because there's no oscillations, there's no missing terms. It's a very kind of simple expression. So it turns out that any series, so the question is sort of what scalar functions could you use also for square matrices? And it turns out that any convergent series is one that has a square matrix version of it. So what does a convergent series mean? What that means is, as I look at the terms in my series, so in the exponential, my terms were 1 and x squared over 2 factorial. As you go along, and so if this is sort of the number of terms, so I'm on the first term or the second term or the third term, there's some value, and that value is sort of arbitrary, but what it means is that with each step, you're getting closer to this value. You're never getting farther away from it. And you can just get closer to it slowly, and it may take infinite terms to get all the way there, but you're getting closer. And it's also okay if it oscillates, as long as it's getting closer. So if I start here, and then the next time I'm here, and then the next time I'm here, and then the next time I'm here, that's okay because each one is closer to the eventual value than the one before it. So you're converging on this series. So, and so often this value of this dotted line is 0, so each term is getting successively smaller, but it doesn't have to be 0 to be convergent. So any series that looks like this and does converge, you can use it for square matrix approximations as well. And let's continue to talk about the matrix exponential because that's going to be the most important to us. So we already saw that if A is a block diagonal matrix, so A looks like A1, A2, 0, 0, where these A1 and A2 are themselves little square matrices, then we saw how you handle this for general functions. So let's just explicitly say an e to the A, if A is a block diagonal, does in fact look like e to the A1 here and e to the A2 here. This is true of all of these functions, but I just want to write it explicitly for this. So now, we have spent time talking about Jordan block matrices and Jordan form matrices, and a Jordan form matrix is just a block diagonal matrix with a series of Jordan blocks. So let's say that A is a Jordan, let's say A is a Jordan block right now. So it's something like this. I'm going to write a 4x4 version because when you look at the 4x4 version, it's sufficient that you can sort of pick out the pattern and you can do all smaller and bigger ones. So a Jordan block has lambdas on the diagonal, zeros below the diagonal, it's got ones on the super diagonal, and then it's got zeros everywhere else. And I can sort of isolate the upper 3x3, and that's a 3x3 block. Here's a 2x2 block. Here's a 1x1 block. It's easy to imagine a 5x5 block. So with the 4x4, you can really pick out the patterns that you're seeing. So let's say this is our matrix that we're interested in here. And just as an exercise, you ought to try and take a matrix that looks like this, A, and square it and see what happens. I mean, and then take that matrix and times it by A again to sort of get A cubed and see what happens when Jordan blocks get multiplied. And what you'll find is that in A squared, you're going to have all zeros down here. You're going to have, for A squared, you're going to have lambda squared, lambda squared, lambda squared, lambda squared on the diagonal. But you'll start getting more and more complicated things up here, like a 2 times lambda or a 1, and you'll sort of start getting what looks almost like a series. I mean, you'll almost start seeing series up here in lambda across here. So Jordan blocks have kind of a special form as they get multiplied by each other. So let's say my function now is I want to look at this function, f of lambda equals e to the lambda t. And you'll sort of recognize this from solutions of differential equations, so it shouldn't be surprising that we're talking about this now. And you'll sort of see how it fits into the bigger picture relatively soon. And so we're going to say, can we take this function, which is well defined in a series expansion, and can we analyze it for a matrix case, e to the at? And again, this is going back to the fact that we're ultimately interested in solving matrix equations that look something like this. This is why we're interested in this sort of function. So it turns out if you do e to the at and just do it completely explicitly, what you're going to get is something that looks like this. Now remember, I'm looking at this 4x4 matrix specifically, and then we can pick up the patterns that fall out of that. So the upper left term looks like e to the lambda t, and in fact we see this e to the lambda t on each of the diagonals. And we get all zeros below the diagonal. And then the superdiagonal row looks like t e to the lambda t. T e to the lambda t. Then the diagonal above that row looks like t squared over 2 factorial e to the lambda t. T squared over 2 factorial e to the lambda t. Then the next diagonal up looks like t cubed over 3 factorial e to the lambda t. And so I gave you a 4x4 Jordan block A, but if that were a 5x5 Jordan block, it would be really easy to see what the next entry should be, right? It should be t to the fourth over 4 factorial times e to the lambda t. And if I only gave you a 2 by 2 Jordan block, you would just take this upper left 2 by 2. So now you sort of got the pattern that any Jordan block of any size, you could take e to the at of that Jordan block, and you could explicitly solve for what it looks like. And because the pattern is so recognizable, you don't ever actually have to do this series math yourself. Once you sort of believe it's true, then you can just sort of memorize this pattern that happens, and you can really quickly pull up the solution of an exponential of a Jordan form matrix. So what if A instead looks like, let's say A now is a Jordan form matrix with two 2 by 2 Jordan blocks. So let's say, I'm going to do something like, like this. So now this is a Jordan block, so let's say lambda 1, 1, and 0. And this is a Jordan block for lambda 2. So I have two 2 by 2 Jordan blocks, and then these are just all zeros. So this is a block diagonal matrix with 2 Jordan blocks. And if I take e to the at of this thing, you start to see the patterns of how this works itself out. So this block looks like e to the lambda 1t, e to the lambda 1t, and then this is t, e to the lambda 1t, 0. In this block, this is just a big 0 block here and here. And then this block looks like e to the lambda 2t, e to the lambda 2t, t e to the lambda 2t, 0. So each of the Jordan blocks individually, when I include them in a function, they just raise exactly like a generic 2 by 2 Jordan block. So now entire Jordan form matrices with sort of arbitrary Jordan blocks on its main diagonal, we can raise those arbitrary Jordan form matrices as an exponent. And so recall that for any arbitrary matrix A, it is similar to a Jordan form, and we do this similarity like some matrix V, Jordan form matrix, V inverse, where this matrix V, its columns are what we call the generalized eigenvalue or generalized eigenvectors of the matrix A, because this came from this idea that A times V is equal to V times J. So V, the columns of A are the generalized eigenvectors of A, and we have this similarity transformation that always exists. So any square matrix A, this is true for, and then J is some Jordan form matrix. So knowing what we know about functions of square matrices now, we know that if we raise this function A, we're going to get V times this function J times V inverse. So basically, we now know how to take e to a Jordan form of t. We've just spent the last slide doing that. So any matrix A, if I want to take e to the at, I can always write that as V times e to the jt, V inverse. So this is going to be a really powerful tool for us, because basically, if I want to raise any matrix A, the exponential of any matrix A, I can find its Jordan form using a similarity transformation. Then I can use the pattern that we know about how you take exponentials of Jordan forms, and then at the last step, just pre and post multiply by the V matrix, and I'll get this solution. So it's a really nice result for us. Let's kind of wrap up by looking at a couple of other nice properties of square matrices that are going to be useful potentially in doing mathematical proofs. So let's begin by sort of writing down what this looks like again in the scalar case. So it looks like 1 plus lambda t plus lambda squared t squared over 2 factorial plus dot dot dot. So we've seen that already. I did e to the x, but now x is lambda t. So now let's explicitly look at that for a square matrix and how we might have to change it. Well, now if A is an n by n matrix, then I start with an n by n identity matrix. And typically with matrices, you multiply the scalar in front of the matrix, so we'll change that to look like that. And the same thing goes for this. We'll say t squared over 2 factorial times a squared. And so this is how we'll kind of modify this slightly to be a matrix version. So we have this series, and this series is always very well defined. And once you have this series, then you can sort of prove a lot of things to yourself from that series. So for example, if I want to take e to a 0 matrix, then I can easily prove to myself that's just the identity matrix. And if I want to take e to the a times t1 plus t2, then this is equal to e to the a t1 times e to the a t2. You can prove that to yourself. You can prove to yourself that e to the at, if I take this thing, which is if a is an n by n matrix, then e to the at is also an n by n matrix. And let's say I invert that matrix. That's the same as e to the minus at. What else can I say? If I want to take the derivative, so the e to the at is still a function of time, so I could take the time derivative of it. So I could take ddt of e to the at. It turns out that that's equal to, and I do this by just going right back up to the series of e to the at and then doing differentiation term by term. And then when I do that and then repack them, I'll see that this is equal to a e to the at. And an interesting thing that falls out is that's also equal to e to the at times a. So you can pre or post multiply the exponential by a, and you'll get the correct answer. And this is sort of a rare thing that happens with matrices, because usually things don't commute in general. But again, this just falls out of differentiating this series up here term by term. Another thing that's interesting, sort of one last closing thought, is we have this this idea of Laplace transforms of scalars. So when you've seen this before in other courses, the Laplace transform of e to the at looks like 1 over s plus a. Well, if we do term by term Laplace transform of this, we'll find that the Laplace transform of this matrix equation e to the at, where this is a n by n thing, ends up being equal to si minus a inverse, which is the matrix equivalent of this 1 over s plus a. Excuse me, this should have been a lowercase a. So this is the matrix equivalent of this scalar equation that you're so familiar with. But again, it just falls out of doing the Laplace transform of this term by term. So I think the big takeaway from this is everything is done in series. So if you ever want to sort of prove something to yourself, you write out the series of the function you're interested in looking at, whether they be exponentials or sines or polynomials, and you do operations on the series and then repack things into sort of a more compact notation.